Hello. So from our previous tutorial module on voltage regulator, in this module, we continue our discussion and we are going to see the analysis of this regulator circuit and a simulation of this regulator circuit. And we know that this is a voltage regulator circuit and it is called as series voltage regulator. We call it series voltage regulator because there is a pass transistor in series with this circuitry from input to the output. It is connected in this fashion and therefore it is called as a pass transistor or series transistor. And what we see here, there is a Zener diode and we have a load resistor RL and we have a resistor R1 which is an input series resistor, and we have this unregulated voltage source. So this value of unregulated voltage source is going to fluctuate due to variations in the temperature, due to variations in the load if we connect the load directly to it, or there is changes due to some noise or disturbance. So that's why we have this arrangement of the circuit. So this class of regulator is called as linear regulator. So all this we have discussed in our previous module. So just refer to that where we will see the block diagram of the linear voltage regulator. In that particular class, you will see the block diagram of series voltage regulator. You will see why it is required, how it works in the block diagram form. And here you are going to do the circuit analysis before you simulate it. So what you see, let's say you have an unregulated voltage supply, which is V1, and it will source a total current I into the circuit. That current is being divided into two parts. Let's say the current flowing through R1 is called as IR1, and the current that is going to flow into the collector of this transistor. So here you have a collector, you have an emitter, and you have a base. This is an NPN transistor. So the current that is flowing into the collector terminal is IC, which is the sum of this current I equal to IR1 plus IC. Now this IR1 comes here and it splits into two parts. That is the current going into the base and the current into the Zener diode IZ. So when the current starts flowing into IZ, and that happens when the voltage across the cathode and the anode exceeds the voltage Zener voltage breakdown of the diode. So this is Vz. So remember, you have output characteristics I versus V, and when you have a voltage in a reverse bias condition, the voltage across the Zener exceeds the Vz, the diode starts conducting a current. So that's your current here. And it is a constant voltage irrespective of the changes in the current from cathode to anode. So that's how now you see this IB is here, and the current that is coming out of the emitter is called as emitter current that subsequently flows into the load, that is the load current IL. When the load current IL flows through resistor RL, it develops a voltage drop across the load resistance, which is the output voltage essentially, or it is also called as load voltage. So you can see now the voltage drops, base is positive with respect to meter. So there is a voltage drop VBE, and you can apply a KVL into the loop, and we see that the output equation, that is let's say VO, output voltage, which is equal to VL, which is VZ minus VBE. So we have seen that. Okay. So what happens if there is a fluctuations into the load and the load voltage changes, whether it goes up or goes down due to anything such as temperature variations or some noise or disturbance that varies the load current, or there is some fluctuation in the input side. So the job of this circuit is to maintain the output voltage constant, which is Vz minus Vb. So output voltage will always be a Zener breakdown voltage minus one drop, junction voltage drop of the transistor, which is Vbe. So let's say Vo goes up, the VO goes up due to some reason, and you want to bring it back to its original value. So if the VO goes up, you see now there is an equation Vz minus Vb, and Vz is constant. So Vb will be adjusted. How? So VO is the voltage at this node. So the emitter potential voltage at the emitter goes up. So Vb, your Vb E is equal to Vb minus Ve. So VO goes up, so Ve goes up. Ve goes up, it means Vbe comes down. So you see, in this equation, we see that if the VO goes up, Vbe is coming down proportionally so that the VO can be brought to its original value. Similar thing happens if the VO goes down, VBE will go up because the voltage at the emitter is going up. And again, the VO will be maintained, which is Vz minus VBE. So this is the understanding about how this circuit will maintain a constant voltage drop across the output if there is some variation in the load current, right? So VBE goes down or VBE goes up. So how this voltage is coming back to its original position. So when we say the VBE is changing, if the output is trying to deviate from its value, so VBE is going to deviate, it's going to change. If the junction voltage of the transistor is going to change, it means the current flowing through the transistor, which is IB, is going to change. And remember, the IE is equal to IB plus IC. So IB is going to increase or decrease, which subsequently going to increase or decrease the IE. And IE is nothing but your IL. So essentially the IL will be modulated, which will modulate the drop across the load resistance. So this is how things will happen. Now, let's understand some more things about input side of the circuit. For example, you see you have this current I that is splitted into two parts, IR1 and IC, and then there is this KVL can also be applied in this loop. So it says that V1 minus IR1 times R1 minus Vz is equal to 0. That is the KVL in this loop, right? So let's say you have a fluctuations in the V1, that is from the input side, and you still want to maintain output voltage constant. So what will happen if the VO is going to fluctuate? It means this current I is going to fluctuate. Therefore, the IR1 is going to fluctuate. IC is also going to vary. So if the IR1 goes to variation, the IZ and IB is also going to vary. So when the IB is varying, IE will be modulated, subsequently IL will be modulated, and the voltage drop across the load will be maintained constant. So this is an ideal situation. So that's all about your circuit analysis. Now, what we have done here is that we have used the SPICE circuit simulator from the library. We have put up all the components and the devices, and from that, we see that we have this voltage source, resistor, transistor, diode, and the load. So we have taken some values. We have taken the voltage regulator diode, voltage reference diode. This is basically a reference element that provides a constant reference voltage in the circuit. And the name of the model is BZX846. So let's right click here and see the properties of this diode. So we see that we have selected this diode from the onsemi manufacturer. It is Zener, and its breakdown voltage is 6.2 volt. So the output is going to be, V output is going to be VZ minus VBE, as we have seen before. So it will be 6.2. So let me check again how much it was. 6.2 volt. Yeah. So it's going to be 6.2 volt. Yeah. 6.2 volt minus 0.7 volt. So it's about 5.7 volt approximately, considering the base to emitter VBE drop of the silicon PN junction of the silicon transistor is about 0.7 volt. Okay, so that's the voltage you are going to get at the output. So having said that, so we have selected diode. Let's check about the transistor. We have chosen an NPN transistor, and we don't mention what is the collector current and the VC and all that time. We just say that it is simple transistor that is going to act as a regulation of the current. Here our load is chosen to be 10 kilo ohm, and R1 is the series resistance is chosen to be 1.5 kilo ohm. So that is 1.5K, as you can see here. And now the voltage source, unregulated voltage source, is about 10 volt. So remember, this voltage, unregulated voltage, whatever the value it is, you got to have the Zener breakdown voltage accordingly. So it would always be the case that when your input voltage V1, which is this one, is greater than or equal to Vz, the Zener will start conducting the current from cathode to anode, and that current is IZ. So we have seen the characteristics of it. Now, since we have constructed this circuit and values have been chosen, let us see the behavior of this circuit by simulating it. So what we do here is that we are going to take the simulation of this circuit. So what we will do is that we will just simulate. So before that, before the simulation, let me just get rid of it. Yeah, so here is the simulate button. So before the simulation, we need to choose what analysis we want to run. So first we have to understand the operating point, DC operating point. It means all the voltages and the currents that we theoretically analyze. We saw the equations, whether they hold true or not. And we can also calculate the values in theory because we have the values available. So we already know what is going to be the output voltage. It is about 5.7 volt. We just saw that. Similarly, the voltage across the diode will be 6.2 volt, and the voltage across the base emitter junction will be 0.7 volt. Voltage across the R1 would be 10 minus 6.2. So it will be 3.8 volt because of the KVL and Ohm's law. So click edit simulation. Now you see, let me just remove this annotations, clear all drawings, and after that we can come back to simulation and edit simulation card. So here we choose the DC operating point. It will compute the DC operating point. It will treat any capacitance as open circuit and inductance as short circuit. Fortunately, we don't have capacitance and inductance in the circuit, at least visually. There are parasitics of the transistors and the diodes in the circuit, but that's the practical model. But we are just taking the ideal case. So syntax for this simulation is .op. Click OK and place it somewhere. So what this simulation analysis will do after running, it will calculate the operating point. It means calculate all voltages and currents in the circuit. So let's run it. Go to simulation and run. And you see now these voltages have been computed. So here first is V in bracket V output. So that is the voltage at the V out node, which is 5.51, which we predicted correctly. That is the Zener draft Vz minus VBE. So nearly same. Now what is the voltage at VNOO2? It is 6.2, which is the Zener voltage at this node with respect to ground. What is VNOO1? This is 10 volt, which is at this node. That is the voltage of the unregulated supply. Now there are ICQ1, IBQ1, and IEQ1. So that's basically the collector current, which is about 0.5 milliampere, and emitter current, which is about 0.55 milliampere, and the base current in the middle, which is about 5.45 microampere. So multiply this value of base current by or just say IC divided by IB will give you the beta, that is the transistor gain. Okay, then you have ID1, the current flowing through the diode is about 2.4 milliampere right here. The current flowing through the R1 is 5.5 milliampere, and current drawn from the supply is about 3.031 milliampere. So you see all these voltages can be computed. I close it. If I right click this net, I can choose this option like highlight net. I can see that and it highlights. If I again right click it, and I can choose this option place.op data level, it will print that value right here. So you see it's 5.5 volt. If I want to monitor the voltage at the cathode of the diode, I right click and I place that. It is about 6.2 volt. You see, it is 6.2 volt. So you can just move it also somewhere. Oh, it's not there. Huh? So place set a label and cancel it. So that is one. Now I want to see the voltage at here at this net. So I right click here, place data, it is 10 volt. So you see the voltage across R1 will be 10 minus 6.2 divided by the value of resistor. That will give you a current. The voltage across R1 would be 10 minus 6.27 volt. Simple. So this is how you can actually calculate all voltages and the currents. If you want to know the currents, you basically place data label at any, but it is printing the output voltages actually, because the currents will be done with this white board. I just simulated this again, and this white note comes with all voltages and the current, so you can have the analysis. Okay, once you close that, these voltages will be printed again. Is there any is there any voltage at the node that you want to print? So you see now the voltage at the base right here and the voltage at the emitter right here. If you take the difference, which is VBE, voltage across base to emitter junction of the transistor, which is 6.27 minus 5.5, and approximately 0.7 volt. Is it? 0.66 volt. Yeah, it is 0.66 volt. So you see this .op command helps us to do such analysis. Now, the output voltage is 5.51, which is as per our equation, and the equation is your VO equal to VZ minus VBE. What if you change the value of, let's say, the value of the load changes? For example, um, let's say you change the value of a load. There is some variation. It goes to about, let's say, 15K, and we'll see what changes happen. So remember, the voltage right now is 5.51 volt. Run the simulation and 5.52 volt, same. So you see that's how the regulation is maintained. Essentially, what is happening is that the VBE is adjusting itself. That is why the base current is being changed, which changes the emitter current, which is nothing but the load current, and the RL variations are still taken into account. What about the input changes? Let's say from 10 it goes to 15, and we'll click here and boom. So we still have constant 5.59 at the output, which is manageable. There are some changes, of course. But what if we just make the V1 fall below VZ? So VZ, remember, is 6.3 volt. So what if we just check this 6 volt? Will it maintain the regulation? Will it regulate the output? No. See, now you got to see that the output voltage is decreasing 5.1 only. It has to be 5.5 or 5.6 precisely, because the Zener diode is falling below the conduction. It is not conducting fully. So you say like 3 volt, for example, and the output voltage will be dropped heavily. So you see you don't have any output voltage, and this Zener is out of conduction. So that's how you can experiment yourself. And similarly, all these values of the currents and the voltages, you can monitor whether the transistor is conducting and which mode it is and all those things. So all these analysis can be done. So remember, this is how the circuit works, and you can actually do the analysis. There is some other analysis, like you can sweep the values of load or values of voltage source and plot actually the output voltage against these variations. We'll see that in a next module perhaps. So hope you like this video. If you did so like this video, comment on it, and share with others for wider reach. And please subscribe to the channel. Till then, stay tuned for more informative and technically rich content. Wish you happy learning.